This program is brought to you by Stanford University. Please visit us at stanford.edu.
All good appetizers must come to an end, and then we move on to the main course. And I see the main course in the back of the room, Professor Bob Twigg. I'm really excited about having him here today because we've never done this before. We've usually just sort of done this hard jump from astrobiology to human space travel. And it's a pleasure to have someone who's more technically oriented than I am. So I will just pass you all over to all the cables and say that we should give a great welcome to Professor Twigg. You're trusting a biologist to hook up your computer?
Oh, absolutely.
Big mistake. There you go.
I really appreciate the opportunity here. Lynn put out a call for people to come and make presentations, and I jumped to the head of the class. I really am excited about what she does. I think that met Lynn about a year or so ago, and she said, you know, we'd like to do something. What can we do? And I think, what was it, within a month we flew a payload for you or something like that. And the things that we do in AeroAstro is, you know, we build satellites, we build other kind of gadgets, but you get to a certain point in building these things, you know, you say, what am I building them for? You know, they go up, go into space, they work, they do nice things, but you come to realize that really what you want to do is, if you can, do science with them. And that's where the real return comes back. So I think the opportunity that we've had to work with Lynn on stuff on the balloon is super, but there's a lot more I think we can do, and today I hope you'll work with me to figure some of that out. But I kind of want to give you an overview of, in the Space Systems Development Lab, you know, how we fumbled to get, how we worked to get where we're at, okay? So what I want to do is talk about the evolution of the program. Should I stand still so you don't have to work so hard?
You're not allowed to move at all.
Okay. Well, I'll stand more in one
Yeah,
spot.
you don't. You can move around.
I just don't like to be planted firmly. Okay, this is where we started. I came here in 1994. I'd had some experience working on satellites at a university in Utah. And they asked me if I wanted to come here and start a satellite program at Stanford, and I'd actually been here in the 60s on the honors co-op program. I went to school, and the idea of coming back to Stanford on the academic side was really pretty exciting to me. So I got here and got a group of the students together that actually had been working on designing satellites for a few years, and so we got together and said, you know, what do we want to do? And, you know, the first thing you do is you start with a vision. We said, we want to build a satellite, and we want to build it, you know, about the size of a lady's large hat box. Now, my wife caught me one day in a presentation. I said, a large lady's hat box. She says, they're not the same thing, Bob. Okay, so this is a lady's large hat box. And why did we want to build it that size? Because I had actually worked on some spacecraft before, and you know, it's pretty small compared to, you know, the big satellites that you do science on, but it was big for us. And we said, well, you know, when we get all worked out, it would look like that. Now, you see it has, what, 8 sides on it? Why do you think we made it with 8 sides? Anybody can guess? No? Doesn't it look cooler than a square box? And that's about the reasoning we used on it, you know? In engineering things, do you like the iPod? Why do you like the iPhone and the iPod? They're cool, right? So, you know, we're kind of the same way in engineering. We're not quite as dead as you think we are. So anyway, we said, gee, it looks kind of cool, you know, put 8 sides on it. And so we decided, oh, well, let's fly a camera, because on amateur satellites, which these are, they had never flown a camera that worked. We had a MEMS infrared sensor in it, which Tom Kenny in mechanical engineering was making. And we decided, well, let's put a voice synthesizer in. Now, you know, you don't hear very much from space. Right? If you ever went outside and listened for satellites, you don't hear a thing, mainly because they're traveling in a vacuum, right? But if you can make it send it down on a radio signal, that would be better. And then we did some other things with it. So now notice, this is to be completed in 1 year. The next year, if we're going to complete one in 1 year, we start a second one the second year. We were a little farther behind. We had a vision, but no concept and didn't know what the payload was going to be. All right. We continued in 1995, and our first one wasn't done, and our second one was far from done. So this is kind of the dialogue that went on with the students, between me and the students. I said, why aren't you done with Sapphire? They said, you don't have a launch. Now that's always the excuse. If you don't have a launch, why do we need to get it done? And I said, you finish the satellite and I'll get a launch. But the student says, we can finish it if you get a launch. So to me, to myself, I said, students don't know about reality. I'm really in trouble here, you know. Okay, so here we are, 1996, going on 3 years. Completed 1 year, nothing. The reality was we're still working on Sapphire, and we're still building on number 2. We don't even have a name for it yet. Okay, but it turned out in 1997, due to Professor Kenny, we had a class that we were developing things called picosats, little teeny satellites, and NASA wanted to launch these things. You see the picture of it. It's like a hockey puck. And they wanted this to launch this out of a satellite spinning. They wanted to do some magnetic field measurements. Okay. Now, to myself, I said, I'm in bigger trouble now. Where did I go wrong with student satellites? You know, maybe I should have picked something, maybe astrobiology, but I don't know anything about that. Did I promise anyone that would get done? How do I get them launched? I got a good excuse. Designing and build satellites are fun and educational. Nobody said anything about launch. Okay. Payload project. Go get a prototype. Got a prototype of the picosat. You've seen it there. And then we had to build a launcher, and I call it semi-operational. This design would have made Rube Goldberg cry. And everybody, I hope, knows who Rube Goldberg was. Is there anybody that doesn't? Okay, so I assume you all do. Well, this was unbelievable, but it actually worked sometimes. We took it down to JPL and demonstrated it, and believe it or not, every time they tried it at JPL, it worked. Murphy generally gets in the road, and that doesn't happen, right? Okay, it worked. Now, how do you get rewarded for success? JPL comes back and says, great job, students. Now we have enough funding from headquarters to do the project. We don't need your help anymore. Oh, that was good news to me. Not good news for the students. Not good news. And JPL says, we are now going to stop funding you for the student project, and we don't want you to work on it anymore. We want all the glory now that you've proved maybe it can be done. Do I like JPL? You've probably heard those stories before. Well, it turned out before this, I had a guy from Aerospace Corporation call me up and he said, Bob, we understand you're working on picosats. We're going to have this conference. We'd like you to come down and give a paper. And I said, that sounds great. We'd like to do that. So I went to Tom Kenny and I said, Tom, guess what? We can give a paper at this conference on the picosat. He said, oh, wait a minute. And I said, what's the matter? He said, we don't want to really do that. That'll upset who? JPL, because they're in competition with the Aerospace Corporation. Don't do that, Bob, or we'll lose our funding. Well, what happened? We lost our funding, right? They just yanked it right out from under us. So within 1 microsecond, I was on the telephone to Aerospace Corporation. It was a really hard decision. All right. So we worked with the Aerospace Corporation. We got DARPA funding. We made a new launcher. We made a new picosat. We finished number 2 and named it Opel for Orbiting Picosat Automated Launcher. Got Opel launched in January of 2000. Ejected picosats. Everybody's happy. We are happy. Do you know what? The funding that JPL got to do their project, they were flying on a rocket. It didn't work. Oh, I was heartbroken. Okay, this is what the launcher concept turned out to be. Just It looked like the cartridge on a rifle. You know, you shove things in, it's spring-loaded, you open the doors and they pop out. There's Opel. We got Opel done. You can see the places up here where the launchers are. Back there, we got Sapphire done too. You know, pretty spectacular. But the way we really got credibility in this is we had Sapphire done enough that they believed that we could get this one done. So having something, at least in the satellite world, almost ready to fly helps you get launches. Okay, Jamie Cutler, I think you've seen Jamie and know Jamie. Jamie was the project manager on this as a student. Did a fantastic job. You see the PicoSat there? That's how big those satellites were. We call them a Klondike ice cream bar. That's about the size they were. Well, we got launched. We got the PicoSats up, a little bit of problem with them, but we got that worked out. And we actually launched them. End of the story? Well, no. One of the things we learned out of it, it took us so long to build those satellites, I was afraid that graduated students would have grandchildren or have children by then, or we'd have grandchildren. So it's not the way to do education. We wanted to get through the complete cycle on it. So we needed to change. Took too long to build and finish, too expensive to launch, fairly costly, something needed to change. Well, this is what we come to the realization. Look at these little Pico satellites. Can we make something that small do anything useful? And the problem with that is it's flat and you can only put solar cells on two sides. If it turns on an edge, it doesn't get any power. So the natural thing was to build a box. Now the way you model satellites, at least the way I did, I had some solar cells, and I said, well, how many of these solar cells can I put on a box? And so I went to Tap Plastics. How many of you know about Tap Plastics? Good place, fun to go to. So I bought a Beanie Baby box. Okay, that was the model. And I tried it and said, hey, that works pretty good. Now, how do we hold it in a launcher? And I said, we'll leave some room on the edges. And that was pretty good. And it was a 4-inch square box. And about that time, Lockheed Martin and JPL had a little problem with dimensions on a Mars mission. Do you remember what that was? Anybody? One of them was working in metric units and the other was working in English. Kind of confused things a little bit. So I said, it's about time U.S. university students learn metrics, right? So I changed that to a 10-centimeter box. Well, what's the difference between 10 centimeters and 4 inches? About 7 or 8 thousandths. About the same. But there's real meaning in making things in engineering. It's a picosat is defined as 1 kilogram. How much does 10 cubic centimeters of water weigh? 1 kilogram, right? So see all the lessons you can learn if you build it right? So that's what we did. So that's the thing. And this become a standard. We worked with Cal Poly to get a launcher, and that become a standard. Okay, there's the launcher, holds 3. This is what Cal Poly come up with. That's one of their satellites on the right. And what's happened today? CubeSat has actually become part of the space industry lexicon. It is really hard to believe. We originally named that satellite, what was it? It was Cube Satellite for College something something. And it was so hard to write, I just gave up and called it CubeSat. Okay, 33 of them have been delivered for launch, worldwide now. We had a launcher in Russia with 14 on. It didn't put them in space, it splashed them all over the countryside out there, so they didn't get into space. But we got 19 of them up there. Of those, no contact with 4, some contact with 5, 10 had full contact. That is really good for a beginning program with things being built by students. This now is a worldwide program, and lots of universities are working. So, you know, is all there is CubeSats? No, you know that more than that. Hey, we like to do things on little balloons, bigger balloons, amateur rockets, and then we get up to what I call a desktop CubeSat, and that's one that works on the desk but doesn't work in space, or you don't put it in space just to learn on. Then there's the LEO orbit CubeSats. Can we send CubeSats to the moon? I don't know why not. Can we go to Mars and beyond with them? If you had a CubeSat. Now this is a CubeSat. What would you, as astrobiologists, put in a CubeSat to do experiments in space? What would you put in that little guy? 1 kilogram. But the cost is about the size of a cheap SUV. It's about $40,000. All right? Anybody have a more expensive SUV than that? Probably, because it costs a lot of money. So as far as space is concerned, going into space, it's pretty cheap. It's throwaway money for some of the agencies. Okay, little balloons. We hook things on little teeny balloons. We have a little thing that we call it CubeSat. And this is CubeSat. And let's see here. Okay. CubeSat is nothing more than a little oscillator, and we can put a transmitter on it. And what it does, can you hear it? If I squeeze its tail, the harder I squeeze, think it's going to take off? All that is a thermistor. So if you want to measure temperature, you just set this someplace and you put a little transmitter on it that I got, you turn your radio on, you hook it up to your notebook computer, and you can measure the frequency of that, and you can correlate the frequency to temperature. So here's a little test instrument that you can do. Fly it on a little balloon, and I'll pass this around. If you want to squeeze the tail, you can. I mean, it'll shock you bad. If you get tired to listen to it, you can just pull that little jumper off. That's a CubeSat. Okay. So here's some students working on a CubeSat. Did you break it? Okay. Here they're going out, hooking it on some balloons, and flying it. We go over to Rancho San Antonio Park and fly them. After we tell the ranger what we're doing. And this is kind of what it looks like. You can look at this profile. And then do bigger balloons. This is the great one. This is the one. We fly something very valuable, Pingpong balls. There are ping pong balls from a grade school in Campbell. There were 500 students put things in those ping pong balls. We told them they were going up to 100,000 feet. There was radiation up there. It was cold and there was a vacuum. Most of the students put candy in it. Why would you put candy in it? We talked about radiation, right? I think some of them thought they could make kryptonite up there. They come back and all they found that it tasted terrible because it had thawed and frozen, thawed and frozen, thawed and frozen. But anyway, that's pretty cool. 300 people, there were 500 students at school that participated in this flight. You can see it go. Launched it near Mount Hamilton. These are the students out on 450 at Durand, talking with radio. They're tracking it there. Went out near Stockton. Balloon broke out there, come back down and landed not too far from the lake. Thank goodness. This is what it looks like up there. Cool. It is just from 100,000 feet. Boy, you can see the curvature of the Earth. You can see the atmosphere up there. It's really a cool sight. Okay. Here's another experiment that we did. We had a payload that we wanted that had GPS in it and had an Iridium telephone. Anybody know what an Iridium telephone is? Or anybody know anything about Iridium? Nobody?
This is different from the KT boundary video.
Iridium is the name of a satellite constellation that was put up several years ago that allows you to use a telephone like a cell phone any place in the world. You don't have to be near a city. So you can use it in space, you can use the North Pole, the South Pole, no matter where you're at. Anyway, we had an Iridium phone in it, and what we were looking for is flying this thing called Reever. And Reever is a re-entry black box recorder. It's to put on pieces of spacecraft that are coming back in. They want to measure the characteristics coming back in. And then what they do is they kick this off. It comes down like a little re-entry capsule. When it gets down low enough, it kicks out a parachute. And then it sends the data that is collected over the Iridium telephone back to whoever's flying it. And so we were testing that to see how well it worked. And got antennas tracking it. This is where the track of it went. This is down by San Luis Obispo there. We clear out in an area out here where there's a bunch of ranches. And so we were determining, we knew exactly where it was because we got data back from the GPS on it. And we wanted to go get it, but we drive along this road and we say, oh, it's over there beyond that pasture in those hills. We know where it is. But there's all of these signs on the road. No trespassing, no hunting, no trespassing. It looked like the farmers in there were hostile. So we decided that maybe rather than us make our own trail, we go to the ranch house and ask the guy if we can go in there. So we go to the ranch house and we see this little house. It was the Foremans House. So I was in charge of this group, so I sent somebody else in to talk to the foreman. I didn't know what they'd do to you, and I was kind of protecting myself. So I sent this other guy in there. And the guy took one of our mentors, it turned out, and they went up to the big house to talk to the big boss. And you see, even on the gate we drove in by his house, it said no trespassing. And this guy walked in the room, and Ron Ross, who was our mentor, said, do you know what he said? He said, no. He said, he told the big boss, he said, hey boss, this guy and some others are out there. Should I go out and shoot them all? They're not hostile. Anyway, it turned out these were really nice people, and they drove us way back up in the canyon where we found our balloon. There it is, hanging in the tree. Just as good as can be. The Iridium on it, the GPS all working, transmitting up to the satellites way down deep in a canyon. And we tracked it. It's really cool. And here shows what the acceleration on it was. You can see it's accelerating as it goes up. The balloon breaks, it drops, accelerates, and then actually slows down when it gets farther down in the atmosphere. And then we do rocket flights. We go out to a place called Black Rock, and students build all sorts of things to put in the rocket. Here's a thing that they built that goes in the rocket that has a parafoil on, and it's supposed to guide itself back to the launch site. Okay, here's students working on things. Last year we had about 95 students out there, and we flew 40 rockets. And these are some of the things they built. Little rovers, autonomous rovers. Now, this could be something that you could use to collect samples if it were on the moon. Okay? Sometimes, I don't think there'll be too many tracks like that on the moon. But anyway, there are tire tracks. Sometimes it's hard to get through them. Here's another one. There's what the rocket looks like. This cylinder there is where we put things. We build things in Coke cans. We just can't stand to throw away containers that look like satellites, so we build things in Coke cans. They get up to 12,000 feet, it kicks them out. You can see the rocket here, the tail end of it. Guy stuffing things down in there. They put it together in 3 pieces with a nose cone. And here it goes. And that thing really takes off. It almost reaches hypersonic velocity going up. Here's one of the things that the students put in it. This is before, this is after it landed. Not too good a shape. I have a video, if we have time, I'll show that later. Now here's another rocket we flew on. This is a little bigger rocket. It's built by students down at Cal State Long Beach. And we had a couple of payloads on it. We had a CanSat in it and we had a CubeSat in it. And this is what the motor looks like, and it's a liquid fuel rather than a solid fuel motor. Okay, it's a pretty big rocket. The tanks weren't completely full. This day they were going to fly it to about probably 5,000 or 6,000 feet. And, oh, that's pretty. That's the neatest looking bird. And there it goes. Now look at, you can see the light spots in the cone there. That's a phenomenon due to the gas velocity that's there. Okay, Uh-oh. 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 It didn't land gracefully. It didn't land as planned at all. But was it a good experience for the students? I didn't see any of them crying out there. But it, you know, sometimes things don't work. But it's a good experience. It was a lot of fun to fly. We got our CubeSat ejected without the parachute. I think it just threw it out the side. Okay. Now, this is something I want to show you to think about. If you would like to fly an experiment on a rocket or a balloon, how many of your students went and followed the balloon when you had an experiment on it? Many of them?
Oh, well, we had a whole group of students who took a second semester directed reading specifically so they could fly on the balloon.
So they could follow the balloons,
Yeah,
right?
I know we have at least one student in here now who wants to get involved.
Okay, all
I
right.
bet we have more.
But what if this was a bunch of fifth graders? Do you think I'd want to take them out to Black Rock? Probably not. I don't like to herd cats. They'd be like cats out at Black Rock. All those little kids, it would drive me nuts. So we're trying to find a way.
And at this class, basically you just put a big cake where you want them to go.
Okay, that's a good idea. Like a cake where there's mice around, right? Okay. So what we want to do and what we're trying to do is the following. If we can't bring the kids to the launch site, can we bring the launch site to the kids? And how can we do that? Well, we got the internet, we got satellite communication, so the idea is this. Out on the playa, out where we launch rockets, we want this trailer set up that has a satellite link back. And it's linking back and will go into a server. And we have all of these little cart here to talk to people in the tent, things out where the rockets land and all kinds of communications and video. This is the little cart here. I know it's a great drawing, don't applaud at all. And this is the kind of guys we work with. Makes you proud, right? There's the trailer that they've got all set up. So actually out on the playa, we don't have cell phone, but we have internet. And then this is the classroom. How can I bring it into the classroom and really do it? If I could, I'd bring the smell of the dust in the classroom, blow it around. We often thought about having a big fan in the back of the room and just dropping dust in front of it so it blew all over the students. They'd know what it's like to get in a windstorm out there. So we want to have a real good experience. Anyway, this is something that we're working on. But, you know, we learn a lot. Absolutely learn a lot. Not only is it fun, we learn lots of things. Is it like a normal class that you teach? Absolutely not. There are things that you do that, you know, it isn't written down that you do problem 5 and 6 today and hand it in. It's much more than that. So there's no big mystery about putting things in space. It's an exciting entry point for engineers and scientists, if I could spell it right. Stimulus to new ideas and technology. And this, you know, you students are our space future. You know, who are we going to have around 10 years, 15 years from now to study about space, to study these kinds of things, which I think are just fabulously exciting. And if it's exciting to you, you're going to put the effort into it. So, you know, this is an opportunity for you. So my question is, what can we do in the world of astrobiology, us engineers over across the street there a little bit? Question is, what do you want to fly? How big is it? How high do you want to go? And how long do you want to be there? Those are questions. I can hear the rumble out there. They're just ready to jump up and tell me, right? What do you want to fly? What do you want to fly?
It's fair since I should put a proposal on this. Well, I mean, there are two sorts of things that we've been doing. One is taking terrestrial organisms up there and saying, all right, you know, can you survive up here? can we get a ladybug or a bacterium without a certain gene to survive going through much of the stratosphere? Because you're really time traveling. You're peeling off the ozone layer. So that's one strategy, is to take terrestrial organisms or DNA or whatever up there and measure what happens to it and use it as time travel. And the other big question is what's already up there. And that's something Bob and I've talked about that we haven't gotten into yet and are desperate to, because that's going to require some instrumentation and being able to prove to people that we don't have contaminants. We've already talked about the red rain in this class. We don't want to be another red rain the second at Stanford, right? So you have to be really careful in these things. And this would be a great time to say that, again, if people are interested, I'd be happy to do another directed reading. We'll get another flight in the spring.
Okay. I'm
I'll
really
tell
looking
you-
for that.
Well, we had half a dozen or so students last year, and
Yeah.
only when I was ready to register the grades, I discovered that only one of them was even taking it for credit. They were just coming because they loved it.
Good. That's
So-
what I like to hear. We've got things that we can build all sorts of things. And I'm going to pass this around because this is absolutely the most uningenious thing I've ever built. And I call it a CubeSat. Every time I press the button, it squeaks. Why would you want to build something like that? Well, look at this. What's it got on it? It's got a light. It makes noise. And you can't probably see it, but I got a little vibrator motor on there that if you set it off in your pocket, people would wonder what's in there. You've got a mouse in your pocket. I'm going to pass this around, and these little things here turn it on faster and slower, but I'll pass it around. Now, what good is this? It's kind of the first thing that you build to learn a little bit about electronics. I have these little jumpers on here so you can take them off and measure voltages and currents and all of those good things. But you know what? I like to build these things. I like to solder. It gives me a lot of pleasure to build things and see them go together and just see them work. So you can tell what enjoyment I have all day long. So that's what you can build. But now, you want to get a little more sophisticated, you say. Okay, well look, here's a processor that you can buy, okay, and look, here's a transmitter and receiver that I can put on it. So I can send this up on a balloon or in a rocket, and I can have sensors on it that measure things. I've got accelerometers. I've got this little thing called a ping, and what that does is measure distance between things, not from the rocket to the ground, but closer things. I've got servos that change things. See, aren't you thrilled?
It's pretty good.
I'm glad I brought it. So anyway, you can do an awful lot with that thing. In fact, I've even got a thing that I can put in the ground station down here that you can send it commands, and it has a text-to-speech interpreter. So I could send it text on the ground. And what I want to do is I want to build a satellite like that desktop we got. You know, I want to build that so I can have it in the room here, and I'll have my little ground station here, and this CubeSat can be talking to the ground station, and I can demonstrate a lot of functions. If I pick it up, the ground station will say, "Bob, be careful." And if I take it over to the window, like this, and I hold it there for a minute, it will say, "I like the sunshine." This is my longitude, latitude. And then I can take it around and I can go over here and I can press a little button that's hidden inside. It comes back and it says, "Oh, you got a picture of a pretty lady." And then I can go over here and take another picture and it says, "Who's that ugly guy?" But what am I doing? I'm demonstrating functional capability. You know, you can do all sorts of things with these. They're just absolutely easy. How many people in here absolutely know nothing about programming or electronics? The whole class, that's just what I'm looking for. I can teach all of you to know something about electronics. If you can press that button and it beeps, you're hired. It's quit beeping?
I put it on vibrate.
You put it on vibrate. There you go. Look, he's learned to turn the knobs already. But what I mean to tell you, this is not as complicated as you think. Now, how many of you can turn the VCR on for your TV? Boy, we got the smartest bunch of people in here. You know, us older folks have a little trouble with that. We have it all written down, and even that doesn't work sometimes. But anyway, we can do these kind of things. Is it important that you learn to build something like this? Not as important as it is to get data. That's my theory. We want you to get data, and we want you to tell us what the data means. All right? Now, I have a school. I need something in return for doing this today.
Oh, I knew there was something coming.
If you don't like this, you don't have to. I have a school in Louisiana with kids that are about 4th, 5th, and 6th. We're going to fly some ping pong balls for them. And I told them, I know this scientist lady at NASA Ames that knows about DNA, and she flies DNA. And some little kid, we have a video conference every Tuesday, and some little kid says, what happens to the DNA? And I said, of course, I don't know. But I know somebody that does, and maybe next week, if I could talk to her real nice, maybe she would be on this video conference with me and talk to the kids of what important things you learn in flying things in space.
As the kindergarten say, it gets a lot of owies.
Owie, yeah. But, you know, if you want to see enthusiastic bunch, these kids are so cute. They're really nice, and I got all their names and all their age, and I check them off every time I talk to them. But, you know, there's so much. Do we need to do anything for kids that are that age? Do we? Hey, they'll all come to Stanford like you, right? What's happening to the enrollment for science at the universities? Going down. Why? Well, they want to join some company to do an IP, right? What's an IP? This isn't a computer class, is it? The initial public offering, you know, they want to go to work for people like Google. Why would you go to work for Google?
They eat lots of money.
Lots of money. Are you motivated by money?
Must be more.
I think, but I think you're motivated by interest in things and how they work and what happens.
No one would be in this class if they weren't.
That is right. So, you know, what I see here is exciting students that want to do things. And we can do them, all right? It turns out I have some money.
Class dismissed.
That we can do some things. Part of it is there's always a catch to it, right? Anytime you work with me, there's a catch to it. The catch to it is we've got to get some younger kids involved. Do you know what the percentage of students that start kindergarten in California graduate from high school? Anybody want to guess?
60%?
60? I got 60. Do I have another number?
92.
92. Have I got another number? Come on, you can guess. That's how us engineers work. We guess at all the answers.
75.
50. 50% of the students that start kindergarten do not finish high school.
What are they doing?
They drop out. Yeah, what are they doing? That's really discouraging. Could you make a difference? We worked with these kids with those ping pong balls, 4th graders, down at this school, and we did some other things with them. We had some mentors go in and do a couple of projects with them, not very much. They have to take a test in the 4th grade, a science test. Each class going through the 4th grade takes a science test. 2005, 20% of the kids were proficient. 2006, 20% were proficient. The ones that we worked with took the test after this sort of thing. 90% of them were proficient. And we didn't do very much. I think it's just paying attention to them and getting excited about these sort of things. They just learn more. And that's what we need to do other places, if we can do that. And I think we can. So, why are you here at Stanford? What happened in your life that said someplace along there, I'm not going to drop out of high school, I'm going to go to a university? What happened? What happened to you? Were your parents behind you with a big foot?
Yeah.
Is that it? Was that your reason?
I always liked school.
You always liked school. You had really good teachers. They kept you motivated all the time. So it was expected that you would do that. Why didn't you drop out?
That just never really occurred to me.
Oh, okay. Did you have something happen to you someplace? Was it just your parents that said you're going to college?
Parents and teachers.
Good teachers, right?
And friends who
And
were
friends.
active.
So you had to follow your friends? Yeah, good. Anybody else have a different experience? That you never thought about going to a university, but something happened in your life that says, hey, that might be a good idea. Do you know what mine is? I was raised on a farm in Idaho, and we milked cows by hand, and we had potatoes. Have you ever picked potatoes?
Never picked potatoes.
Oh, you just don't know what you mean. In those days, they had this thing that come along, dug the potatoes up, and they were laying in a row. And so you took this basket, and you picked these potatoes up, and you put them in this basket, and then you dumped them in a sack. Do you know how your back feels after a day of doing that?
I can't even imagine.
Not very good. And how many people in here know what baled hay is? Okay, it's that stuff you feed the cows, it's square. How many of you have went out and hauled that? You lift it out on the field and you put it on the truck and you stack it up and then you get in and you stack. How many have done that? If you'd done that, you'd probably be here too, because I figured there was a better way to make a living than to do that sort of thing. But I have a lot of respect for my dad. He did that as a living, and he liked it, and that was fine. And I thought it was pretty good, but I didn't want to do that. You know, look at my back. It's much weaker than my head. Well, I'm not sure about that. So anyway, that's kind of why I got excited about technical things. Somehow it got away from me, and I ended up going to college. Nobody else had gone to college in my family. But I've had a ball. I've just had a ball. What kind of job can you have that your wife calls you up and says, aren't you coming home tonight, dear? It's dinner's on the table. Oh, is it that late? Rather than watching the clock to have to rush out the door when the clock hits quitting time. Are you having any fun here at Stanford? It's cool, huh? College time is cool. And other times are cool. I think you still have fun.
Wow.
Frustrated sometimes, but she has fun. But NASA takes very good care of her. Okay, I've done enough poking and jarring on you today. So let's do some experiments, okay? Let's go fly something. You know, we can build something and fly it on a balloon from the sidewalk right outside here. And we can put data collection transmitters on it so you can get the data back. And what do you want to know? If you could send a balloon to 40,000 feet, what would you measure on it? Now don't give me anything real big, because I got little balloons.
Well, because we've now been up to 95, so 40,000, I guess I want to know what's there. What's already there. That's
What's that 40,000?
Yeah.
We can do
747.
that from right out here.
747.
We can make things that have GPS on them, so it'll tell you where they are, what their altitude is, and where to go recover it from somebody's house when it comes down. Okay,
See,
so
what
we
need
can
is
fly
a clean
this.
capture system so that we're sure it's not a contaminant.
We got to make sure that we can't do that. We want to make sure that whatever you have takes care of itself. It's very difficult to run and catch one of these things coming down. But we can do it, right? Okay. So how many of you want to fly something? Oh, yeah, got a few hands here. No? Okay. I don't want to commit. Yeah. Didn't you get a thrill when you pressed the button on this? Okay.
I'll tell you, there's not much more exciting than going to a launch.
It's pretty cool, huh? It's really cool. I think I'm about done. So let's go do it. Okay? Thank you.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.